On June 23, 2025, in a conference room in Washington, D.C., the Vera C. Rubin Observatory did something no telescope had ever done on its opening day. It stopped the room cold. A group of scientists stood in front of a screen and waited for the room to go quiet. The moment the image loaded, nobody gasped. The room went silent. What was sitting on that screen was not a photograph. It was 10 million galaxies, captured in a single frame, more than half of them never seen by a human being before that exact second. And that was only the opening shot. In that same short window, this same camera discovered over 2,000 asteroids nobody had ever tracked. It photographed nebulae so faint that older telescopes simply could not gather enough light to see them at all. It did all of this while running what scientists were calling, at the time, only a test. This is the story of Vera Rubin's first images, the day they stopped the astronomy world in its tracks, and why researchers are still trying to process everything 10 hours of test data turned up. Let's start with where this thing sits, because the location matters more than you'd think. The observatory sits on top of Cerro Pachón, a mountain in central Chile that climbs to roughly 8,900 feet above sea level. Dry air, dark skies, almost no light pollution for hundreds of miles. It is, quite simply, one of the best places on the surface of the planet to point a camera at the sky and not have the sky point back with interference. Construction began back in 2014. The project was originally called the Large Synoptic Survey Telescope, a name only an engineer could love, until it was renamed in 2019 to honor the astronomer whose work made the entire mission possible. We'll come back to her, because her story is the reason any of this exists in the first place. For over a decade, the observatory was just a promise, a mountain, a construction site, a camera being built piece by piece in labs scattered across the globe. Then, in the final weeks before the public unveiling, the team hit a problem that almost nobody outside the control room ever heard about. The camera was overheating. Not a minor glitch, not a settings issue. The literal physical instrument, the most advanced digital camera ever built by human beings, was running hot just weeks before its public debut, and the scientists on site had to fix it live, on the mountain, with the clock running. They fixed it. And on June 23, 2025, the world found out what waiting 30 years for a camera actually buys you. Here's the part that should genuinely surprise you. The images released that day were not built from days of observation. They were not built from weeks. The single most famous image released that morning, the one showing 10 million galaxies, was built from just over 10 hours of test observations. 10 hours. To understand why that number is almost absurd, you have to understand what this camera is. At its core sits an 8.4-meter telescope called the Simony Survey Telescope, connected to what is, without exaggeration, the largest digital camera ever constructed for astronomy. Every image it captures covers an area of sky equal to 45 full moons side by side, not one moon. 45. Light bounces off 3 separate mirrors before it ever reaches the camera sensor. A design built specifically to gather as much faint light as possible from the widest possible patch of sky in the shortest possible time. And once the real survey begins, this system is designed to step through the sky roughly 1,000 times a night, photographing new patches every few seconds, covering the entire visible southern sky once every 3 to 4 days. But on June 23rd, none of that had started yet. This was a preview, a demonstration. A proof of concept, and it still produced numbers that made astronomers stop scrolling through their own data and start double-checking it. Let's talk about the first image that broke the internet that morning, a small section of something called the Virgo cluster. If you're not an astronomer, the Virgo cluster is a dense region of the sky packed with galaxies, close enough and rich enough that it's one of the classic targets astronomers use to test a new telescope's capability. Rubin pointed at it, gathered a little over 10 hours of data across 7 nights, and stitched the result into one image. Inside that single frame, approximately 10 million galaxies. Sit with that number for a second, because it's easy to read past it. 10 million galaxies, not stars, galaxies. Each one containing, on average, hundreds of billions of stars of its own. Each one of those stars potentially hosting its own planets, its own moons, its own version of a night sky looking back at us that we will never see. And according to the observatory's own team, that jaw-dropping number was only about 0.05%, 1/20th of 1%, of what Rubin expects to eventually capture. Across its full 10-year mission, this observatory is projected to image roughly 20 billion galaxies and around 40 billion celestial objects total. We opened the door for 10 hours, and the room behind it was already too big to see the walls, but the galaxy count wasn't even the detail that unsettled scientists the most. It's what was hiding in the fine print of that same image, something known as a photobomb, though calling it that almost undersells what it was. Layered into the Virgo cluster frame, astronomers spotted 2 prominent spiral galaxies caught mid-structure and 3 separate galaxies caught in the act of merging together, colliding in slow motion over what is, cosmically speaking, an instant. Merging galaxies are not rare in the universe, but catching several of them, clearly resolved, sitting inside a single test image from a camera that had barely been switched on, is the kind of coincidence that makes scientists nervous in the best possible way. Because if a 10-hour test can accidentally capture multiple galactic collisions in one frame, the obvious question becomes unavoidable. What does a camera like this find once it isn't accidental anymore? Once it's pointed, deliberately, at the same patch of sky over and over for 10 straight years? We'll get to that. But first, I want you to see what this camera did somewhere completely different in the sky, somewhere that had nothing to do with distant galaxies at all, and everything to do with something much closer to home. Roughly 4,250 light years from Earth sit 2 enormous clouds of interstellar gas and dust known as the Trifid Nebula and the Lagoon Nebula. Both have been photographed before, by other telescopes, for decades. Neither one was considered a mystery. Stick with this one, because what came back didn't just add to the record, it rewrote it. Then Rubin pointed its camera at them. The image released that morning combined 678 separate exposures, stitched together from just over 7 hours of total observing time. And what came out the other side did not look like a nebula photograph anyone had seen before. Clouds of gas that older instruments rendered as faint smudges suddenly showed structure, layered pinks bleeding into deep orange backdrops, filaments of dust visible in detail that simply hadn't been resolved at this scale before. One researcher watching the reveal described it simply: "It's a great instrument. Its depth and its field of view will let us take images of even the faintest stars. We are truly entering a new era." That's not marketing language. That's a scientist who studies galactic structure for a living, looking at a test image and using the words "new era" without hesitation. Here's why that phrase matters more than it sounds like it should. Every telescope before Rubin had to make a trade-off. You could go wide, or you could go deep, but rarely both. Wide-field telescopes could scan huge patches of sky quickly, but they missed the faint stuff. Deep telescopes like Hubble could capture extraordinary detail, but only by staring at a tiny sliver of sky for a very long time. Rubin was built to refuse that trade-off entirely. Wide field of view, extreme depth, extreme speed. All 3 at once in the same instrument. And the nebula image was the proof, a target that had already been photographed dozens of times by other observatories, rendered in a way nobody had managed to capture before, using barely 7 hours of data. If 7 hours of test observation could do that to something we already thought we understood, stay with me, because the next discovery from that same 10-hour test window is the one that made headlines for a very different reason. It has nothing to do with galaxies or nebulae. It's about rocks, moving ones. And there were a lot more of them than anyone expected. In those same 10 hours of test observations, spread across just 7 nights, the Rubin team discovered 2,104 previously undetected asteroids in our own solar system. 2,104. In 10 hours, during a test. 7 of those newly found objects were classified as near-Earth objects, meaning their orbits bring them into our cosmic neighborhood. To be clear, none of them pose any known threat. But the number itself is what stopped astronomers cold, because ground-based asteroid surveys have existed for decades, and finding even a few dozen new objects in a short observing run is normally considered a solid night's work. 2,000 before its real mission had even begun. To understand why that number is so disruptive, you have to understand how asteroid hunting has traditionally worked. Most surveys operate the way a photographer works: point, focus, capture, done. One image, one moment, frozen in time. If an asteroid happens to be in frame and happens to be moving fast enough to stand out against the background stars, you catch it. If not, it stays hidden, indistinguishable from the millions of static points of light around it. That's not how this camera works. It was built to return to the same patch of sky again and again, comparing what's there now to what was there before. A dot that shifts position between images isn't a mistake to be cleaned up. It's the entire point. It's a target. Scientists at the observatory put it plainly during the same briefing where the images were unveiled. The amount of data gathered by Rubin in just its first full year of operation is expected to be greater than everything collected by every other observatory on Earth combined. Read that again, because it is not a metaphor. One instrument, 1 year, more raw data than the accumulated output of the entire rest of the field. And once the full 10-year survey begins in earnest, scientists expect the asteroid hunting rate to scale dramatically beyond what those 10 test hours produced. We are talking about a machine that, in its infancy, before it had even learned to walk, casually found more new asteroids in a single test run than some entire research careers managed to catalog. Before we get to that, there's one more piece of the June 23rd release that most people scrolled straight past, and it might be the strangest part of the entire morning. Alongside the images, the observatory quietly launched something called SkyViewer, an interactive app that lets anyone, not just astronomers, zoom freely through the actual 10 million galaxy image at their own pace. Guided tours, freeform exploration, the whole thing sitting in your browser. That alone would have been a solid feature release on its own. But buried inside SkyViewer was something stranger, a sonification tool, an option to translate the colors and brightness of galaxies into sound, letting anyone drift across the image and effectively listen to the structure of the cosmos as an ambient, never-ending soundscape. Think about what that means for a second. A public research instrument released on day one that turns raw astronomical data into something a person with no training at all can explore with their ears instead of their eyes. Scientists weren't just handing over a photograph, they were handing over an instrument the public could explore, live, on the same day the professionals got their first look. That single decision tells you something about how the team behind Rubin sees this project, not as a black box that spits out papers years later, as a live, ongoing broadcast of the universe that anyone can tune into. Now, back to the asteroids, because there's a layer to that number that makes it even stranger than it already sounds. 2,104 new asteroids in 10 hours doesn't just mean the camera happened to catch some rocks drifting past. It means the detection software, running for the very first time on live data, had to correctly identify every single one of those objects as something that had moved between exposures. It had to cross-reference each one against every known catalog of existing asteroids, confirm it wasn't a data artifact, a satellite, a cosmic ray hit, or a sensor glitch, and flag it as new. All in real time, all during a test run, all while the camera itself had been overheating weeks earlier. That is not a small technical footnote. That is the entire detection pipeline, the software brain behind the camera, working correctly on its first real attempt, at a scale nobody had fully rehearsed at once. Engineers plan for failure in situations like this: bugs, false positives, missed detections. Instead, the system's first real night of operation produced a number that took some researchers days to fully verify, simply because nobody expected to. Need to double-check a total that high from a test. So here's the question worth sitting with before we go any further. If 10 hours of imperfect, early overheating camera test data produced 10 million galaxies, multiple galactic collisions, a nebula rendered in unprecedented detail, over 2,000 new asteroids, and a detection pipeline that worked flawlessly on its first real attempt, what happens once this thing is actually running at full strength for 10 straight years without stopping? That answer is coming. First, meet the person this telescope is named after, and the mystery she spent her entire career staring into. The observatory is named after Vera Rubin, an American astronomer, whose work in the 1970s upended the rules of physics, even though almost nobody outside her field noticed at the time. Rubin spent years studying the rotation of galaxies, measuring how fast stars at the outer edges moved compared to stars near the center, and the numbers didn't add up. Based on the visible matter inside those galaxies, stars orbiting near the edges should have been flying outward, flung off into space entirely, the way water flies off a spinning bike wheel. Instead, they stayed locked in orbit, moving, as if something invisible was providing extra gravity nobody could see or measure directly. That invisible something is what we now call dark matter. And Rubin's observations became some of the strongest evidence in history that it actually exists. She never lived to see a telescope carry her name into operation, but in a very real sense, everything you just watched happen on June 23rd, 2025, the galaxies, the nebulae, the asteroids, all of it exists because one astronomer refused to accept that the number she was seeing simply didn't matter. Pay attention to this one, because this is where the story stops being about pretty test images and starts being about the actual reason this instrument was built. Here's the deeper mission hiding underneath everything else this observatory does. Every star, every planet, every galaxy, every human being who has ever lived accounts for only a small fraction of everything that exists in the universe. The rest, the overwhelming majority of it, is dark matter and dark energy, two forces that dominate the cosmos and that scientists still cannot directly explain. Hunting for both is the whole reason the instrument exists. By measuring how galaxies bend and distort the light passing near them, a technique called gravitational lensing, and by tracking the distance and structure of billions of galaxies through something called photometric redshift, scientists expect Rubin to eventually map roughly 4 billion galaxies in enough detail to chart where the invisible mass of the universe sits. And dark matter is only half of that puzzle. The other half, dark energy, is the mysterious force that appears to be causing the expansion of the universe to accelerate rather than slow down. Scientists still don't know what it is, where it comes from, or whether it will keep pushing the universe apart forever. but by tracking hundreds of thousands of a very specific kind of exploding star every single year once the full survey is running, Rubin is expected to give researchers one of the most detailed tests ever conducted of whether dark energy behaves like a fixed constant, or whether it has been changing throughout the history of the universe. If it turns out to be the second option, that would rank among the most significant findings in the history of physics, not a footnote in an academic journal, a rewrite of how we understand the fate of everything, including whether the universe expands forever, slows down, or eventually tears itself apart at the seams. And here's what makes that mission personal rather than abstract. Vera Rubin spent her career fighting for a hypothesis that most of her peers were reluctant to take seriously, an invisible substance nobody could see, detect directly, or hold in a lab. She didn't have a machine like this one. She had a spectrograph, a handful of galaxies, and a stubborn refusal to explain away numbers that didn't fit the accepted model. It took decades for the rest of the field to catch up to what her data had already been showing. Now there's a machine on a mountaintop in Chile carrying her name, built specifically to finish the argument she started, not by staring at one galaxy at a time the way she had to, by mapping billions of them simultaneously, night after night, for 10 uninterrupted years. So step back and look at the full picture one more time. On the morning of June 23, 2025, a team of scientists in Washington, D.C. loaded a single image onto a screen, and inside that one frame sat 10 million galaxies never fully cataloged before, including several caught mid-collision. In the same release, a nebula that had already been photographed for decades appeared in a level of structural detail nobody had achieved before, built from barely 7 hours of data. And quietly, almost as a footnote, the same test run turned up over 2,000 new asteroids in our own solar system. 7 of them close enough to be classified as near-Earth objects. All of that from a camera that, weeks earlier, was overheating on a mountaintop in Chile. We spent centuries looking up at a sky that seemed finished. Fixed constellations, familiar stars, a universe so vast and so slow that a human lifetime never felt long enough to catch it changing. Vera Rubin's observatory proved, in a single 10-hour test, that the sky was never finished. We just never had an instrument wide enough, deep enough, and fast enough to catch it in the act. And this was only the preview. The real 10-year mission, the legacy survey of space and time, was still months away from formally beginning when these images were released. This was the warm-up, the test run, the overheating camera on the mountain fixed just in time. Here's the real question, and I want you to sit with it before you go. If 10 hours of test data produced discoveries this significant, 10 million galaxies, colliding galaxies hiding inside them, a nebula rendered like never before, and thousands of new asteroids, what happens across 10 full years of continuous observation? What does a telescope built to give the sky a memory find once it's had time to actually remember something? We are not just looking at a new set of pretty pictures. We are looking at the opening frame of a 10-year film of the universe changing in real time, and we've only seen the first 10 hours of footage. If this kind of story pulls you in, the way a single test image rewrote what we thought we knew about our own night sky, make sure you're subscribed. Because this observatory is going to keep making headlines for the next decade, and you don't want to miss what it finds next. Drop a comment below and tell me which detail from this video surprised you the most. The 10 million galaxies hiding in a single test image, the 2,104 asteroids found in 10 hours, or the nebula that looked like it had never been photographed before. And if you want to go deeper into what happens once this telescope's real mission actually begins, there's another video linked right now that you need to watch next.